Okay, so let's move on to um, the structure and properties of matter. Structures and properties of matter. So for this subtopic, we'll be looking at the how matter is, yeah, and its constituent being atoms. And also we'll look at its properties as well. So there are some early theories that we have to consider before we can move on. So the first one is the Democritus. So early theories about atoms. Democritus suggested the particulate nature of matter. He called it atom. So Democritus was the first person to suggest that the particulate nature of matter, which is called atoms. So Democritus was the first person to bring that idea that the particulate nature of matter is called what? Atoms. Then Aristotle proposed that matter was continuous and not composed of smaller particles. He named it hale. So Aristotle, that's for Aristotle. Aristotle also said matter was continuous and not composed of smaller particles. Yeah. So that was for Aristotle. So Aristotle named the continuous matter hale. Then first was John Dalton was the first to put forward a scientific theory on the physical and chemical properties of the atom. So you can see that Democritus and Aristotle, they didn't consider the chemical and physical properties of the atom, but John Dalton did that. So he was the first to put forward a scientific theory on the physical and chemical properties of the atom. Proposals based on the law of definite proportion and law of conservation of mass. So for John Dalton, he based on the law of definite proportion and the law of conservation of what? Mass in his research, and he based on that one to give us that okay, for matter or the atom, he will consider it both what physically and what chemically. So Dalton's atomic theory or Dalton's theory. So Dalton's theory, in some books you can get 5, and for this one we'll be looking at 4. So elements are made up of small indivisible particles called atoms. So these are the theories that Dalton proposed. So the first one is elements are made up of small indivisible particles called atoms. So meaning we have element as a whole, and the things within that element is called what? The atom. The smaller things that we cannot break down is called what? Atoms. So the difference between element and atoms is that elements, without atoms there won't be any element, and without element there won't be what? Any atoms. So atoms makes what? Element. But you see, when we are using these words, we normally use it interchangeably. You can see element, you can see atom. Yeah. But atoms mix up what? Elements. And atoms can neither be created nor destroyed. Atoms of the same element are identical with identical mass or size and the same physical and chemical properties, and postulated that the atoms combine to form compounds in simple ratio. So these are the theories of Dalton. So Dalton, after considering the chemical and physical properties of the atom, these are some postulates he was able to bring about. And with this postulate, there were some scientists who also made a research and delve into it that okay, this is what Dalton did. And after their research, they found out that there are some limitations concerning some of um the postulates. So the first one is the indivisibility of the atoms. So Dalton proposed that atom they can be broken down, but the limitation is that there are some existence of subatomic particles like protons, neutrons, and electrons. And these subatomic particles, they are gotten from atoms. So when you break down atom, you can get the electrons, then protons and stuffs. So what that thing said, it was incorrect. That was the first one. The second one was a further breakdown of subatomic particles into elementary particles called quarks and leptons. So when you further break the electrons, the protons, you get quarks and what leptons. Impossibility of creating atoms. So that thing said the atoms can either be created or destroyed, but that isn't true. Through radioactivity and fusion reactions, we can produce new atoms. So Dalton's theory was wrong. The last one was the presence of isotopes. The presence of isotopes. Atoms of the same element can have different masses. Hydrogen has three isotopes. So Dalton said atoms of the same element have same masses and they are identical, but it's not true. But with the presence of isotopes, they are elements of the same um isotopes are atoms of the same what elements, but they have different what masses with the same what atomic number, but they have what different what masses, but they have the same atomic numbers. But that thing said they have the same atomic numbers and they have the same mass numbers, but that isn't true because isotopes they have same atomic numbers and different what mass numbers. So models of atomic structure. So there are some scientists who propose how um the atom is. Yeah. So each and every scientist made his or her research and brought about, okay, for me this is how the atom looks like. For me this is how the atom looks like. Do you get it? Yeah. So the first one we will consider is a John Dalton. So John Dalton said the atom is small, indivisible, hardball models. Yes, so John Dalton's model of the atom can also be called the billiard ball model. So he said the atom is like a hard ball, yes, small indivisible hard ball. J.J. Thomson said it's a plume padding, a watermelon model. Yes, so J.J. Thomson was like, okay, for me, after making my research, I can see that the atom is like a watermelon. Yes, a plum pudding. Plum pudding, I think, is a dish. Yeah, it's a dish also. And Ernest Rutherford came about the nuclear atom model. So for Ernest Rutherford, for his model, you can see the nucleus, the electrons, the protons. You get it? Yeah. And then Neil Bohr also brought about the planetary model. So for Neil Bohr, you can see that his model of the atom, the structure is like a planet. Yes, that's what we call a planetary model. Schrodinger Erwin also came about with the wave mechanic model. Yeah. So when you take the wave mechanic model, by the help of the wave mechanic model, we came to know about orbitals. Yeah, and orbitals they can be defined as the volume of space around the nucleus, within which there is 95 percent probability of finding an electron. So orbitals they are more or less like the shells. Yeah. When you draw the structure of the atom, the orbitals they are like the shells. So within the shells you can see what electrons. You can see the electrons. And also for the wave mechanic model, that's where the uncertainty principle was proposed, that which is it is difficult to determine the position and momentum of an electron at the same time. This theory was proposed by Werner Heisenberg, and Louis de Broglie also suggested the wave particle dual nature of the electron. So the wave mechanic model that Schrodinger Erwin postulated, he combined the ideas of Louis de Broglie and Werner Heisenberg. to bring about what the orbitals in his own mechanic model or his own model. Fast forward, we will be looking at quantum numbers. Quantum numbers. So for quantum numbers, we have four types. We have principal quantum number n. The symbol is n. We have orbital or azimuthal quantum number, which is L, and we have magnetic quantum number, spin quantum number as well. For principal quantum number, it talks about or it describes the energy level of electron and the closeness of electron to the nucleus. So if you have n to be equal to 1, and you see when you arrange the shells, we have the K shell, the L shell, M and what N. So four shells. So the first shell is K, then second L, M and N. So K shell is the same as N equal to 1. L shell is equal to N is equal to 2, N is equal to 3, then N is equal to 4 for the N shell. So for principal quantum number, when you have an electron on the first shell, when you have electron on the first shell, that's N is equal to 1. It means the electron is very closer to the what? Nucleus. And since the electron is very closer to the nucleus, it will be very hard for you to pull the electron away from the nucleus because the nucleus will try and attract the electron. So it makes the electron have a higher energy. So in an exam or in any work that you do, when you have n is equal to 1 and n is equal to 3, then you are told to describe or give the one with the higher energy. It's definitely L is, and n is equal to 1 because those electrons in there, they are in the first shell and they are very closer to the nucleus, and also they have higher energy because you have to get more energy before you can pull them off. Yes. So the maximum number of electrons is calculated by 2m squared. That's the formula where the number of energy levels is the n. So as I said, the energy levels are the K, L, M, N, and each of them is designated with n is equal to 1 for the first one, K, M, L is equal to n is equal to 2. So for the L shell, its principal quantum number is n is equal to 2. That's it. So if you are told to find the maximum number of electrons, you will just insert the n value there. Yes. But when you are told to find the number of electrons that the shells can um, contain, the K shell contains 2. All of them contains 888. But when you are told to find the maximum number, that one you use the formula. So when you use the formula, the first one you get 2 for the K, 8 for L, 16 for M, and 32 for what? N. So that's it for principal quantum number. Orbital or azimuthal quantum number L. It describes the shape of the orbitals. It starts from 0 to n minus 1. So you can draw this table where L values when 0, L is equal to 0. It means the orbital is the s orbital. 0 maps to s orbital, 1 maps to p orbital, 2 maps to d orbital, then 3 maps to what? The f orbital. So whenever L is equal to 0, you know that the orbital is what? S orbital. For s orbital, it has no direction. Yes. So for magnetic quantum, for azimuthal quantum numbers, they describe the shape of the what? Orbital. So for example, when n is equal to 1, it means L is equal to what? 0. Because it starts from what? 0. It starts from 0 to n minus 1. So let's look at n is equal to 2. So when n is equal to 2, it means you have to get two numbers. For the L value, you have to get two numbers, which is 0, then n is equal to 2. So 2 minus 1 is what? 1. So we get 0, 1. 0 is s orbital, 1 is what? P orbital. n is equal to 3, meaning you have to get 3 values for the L values, and 3 minus 1 is equal to what? 2. And previously when n was equal to 2, we had 0, 1. So we will just add the what? 2 to the what? 0, 1. That's why we have L to be equal to 0, 1, 2. The next one is the magnetic contour number. It describes the orientation of the orbitals in space. The orientation. So you use the idea of the orbital or azimuthal contour number to solve for the um magnetic quantum number. So for the orbital orientation of the orbitals, you can see that for this one, the mi values, after getting the L values, the mi values, you have to get both the negative and the negative value for it and the what positive side for it. So for example, when n is equal to 2, L is equal to 0, 1, mi is equal to negative 1. So the non-zero they get, you have to write it negative value, then you write what? The positive value again. You get it here. So that's how it is. So for the magnetic quantum number, just know how to solve for the L, that's orbital quantum number. When you get the L, for the L, the other non-zero they get, for the non-zero they get, you write the negative value and also the positive value. So let's look at the n is equal to 3. For n is equal to 3, you can see that we have L to be equal to 0, 1, 2. So when I'm writing the mi value, I will start from 2. Then I'll write negative 2, negative 1. Because negative 2 is the smallest, yeah. So we start from it. So you have to write both the negative values and the positive values for the mi. So we get negative 2, negative 1, 0, 1, 2. So the orientation is just about the number of orbitals in it. So you can see that p orbital, it has 3 suborbitals. That's why for the n is equal to 2, we have negative 1, 0, 1. P orbital, we have 3 suborbitals. D orbital, we have 5 suborbitals. That's the meaning. So the number of orbitals, that's why we call the degenerated what? Energies. So basically that's what the magnetic quantum number is about. For the spin quantum number, you see when you draw the electronic configuration, that arrows, the arrows, one will be going up, one will be going down. So one is in the clockwise direction, one is in the anti-clockwise direction. So for the spin quantum number, it determines the clockwise-ness of the electrons in space. So the first one, that's so for spin quantum numbers, the values that you deal with it is the negative half to what? Positive half. So the first one that will go up is a negative half, then the second one that will go down is a what? Positive half. That's it for the spin quantum number. For spin, it just shows the anti-clockwise-ness of the electrons and the clockwise-ness of the electrons after drawing the um, electronic configuration. So you can see an example here. You see for the for the configuration, see the arrows, one is up, one is down. Yeah, that's what um I'm trying to talk about. For the electronic configuration, we have two approaches to go about it. Electrons, they are arranged in shells using only the principal quantum numbers. So that's when you have the 1s2, 2s2, 2p6 and those stuffs. And the electrons are arranged in shells using the 4 quantum numbers. So you can arrange it in shells to when you draw the circles. Yes. We have some rules guiding these various um configuration. We have the Avbau's rule, Hans rule, Pauli's exclusion principle. So Avbau's rule talks about for electrons, we fill the energies, or if we start filling from low energy level. So in filling electrons in orbitals, you start from the one with the what? Low energy levels. Hans rule say that degenerated orbitals are filled singly with electrons to maximum before pairing them up. So for Hans rule is stating that, for example, if I have a p orbital to fill, I will fill the p orbital, the 3 orbitals, with just one single electron, one before I pair them up with the other electron. You get it here. So degenerated orbitals, they have degenerated orbitals, they are filled singly with electrons before pairing them at Pauli's exclusion principle says no two electrons in an orbital will have all quantum numbers being the same. So basically, you can't have two electrons in one orbital with the what all the four quantum numbers. You can't have all of them with what all the four quantum numbers. That is the principal, orbital, magnetic, and what the spin. And also, um, no two electrons can fill no two or more electrons. So for Pauli's exclusion principle, it also states that no two or more electrons can be in the same orbital. So you can have three electrons in what one orbital. Yes. So that's the approach. So you can see here the first approach is the principal quantum numbers. Second approach, yes, all the four quantum numbers. So you can just take a view of it.